Hi and welcome to this channel. In this video we'll be discussing the Hartree-Fock theory, which is a subject of computational physics. It's a computational method that can be used to get results approximately of certain atoms, molecules, solids, etc. So we'll be giving you a background on the theory and how one should be thinking when they are looking or when they're dealing with this particular computational method. Without further ado, let's go. Now, let us get into it. So we see that the method in question is a simplification. The theory of the Hartree-Fock is just a simplification of the many electrons moving in a potential field problem. And the systems of interest that we are dealing with are atoms, molecules, and solids. And does not just consist of the electrons, but also the nuclei, where each particle moves in a field generated by other particles, which is what we are saying on the second point. As a first approximation, we may employ the Born-Oppenheimer approximation. What is that? It is an approximation where the nuclei is assumed to be fixed. This is justified by the fact that the nuclei is many times larger than the electrons. To be specific, 1,835 times much larger. Therefore, it remains for us only to solve for the electronic structure and not to worry about how this particular nuclei affects the electron, the approximations, or affects the method. So we won't have to include any calculations with regards to the nuclei. In other words, to simplify a complex problem and make it much simpler, where the only goal is to solve for the electronic structure, hence leading us to an approximation theory that can approximate the behavior of certain atoms, molecules, solids, etc. But of course, the Hartree-Fock method itself needs to be explained in much more detail. So we have that the Hartree-Fock method is a variational type method in which the wave functions of the many electron system takes the form of an antisymmetrized product of one electron wave functions. So we've got the wave function that describes the whole many electron system is but an antisymmetrized product of single electron wave functions. Why is how at all is this possible? This is possible because or due to the fermionic nature of these particular electrons. They are fermions, therefore it's possible for us to then have their one electron wave functions and have them antisymmetrized in a product. Therefore this leads us to a system of many electrons that we can then describe in a variational type method. It is also due to this antisymmetrization restriction we have just imposed that we have an effective Schrödinger equation. Now this effective Schrödinger equation is for individual one electron wave functions. So we will call these one electron wave functions orbitals. Now we have that the potential is determined by the orbitals occupied by other electrons. So these one wave electron wave functions are going to be referred to as orbitals. Orbitals also refer to, say, in an electron or in an atom, we've got a cloud of electrons where these electrons occupy particular energy levels, and again those are particular orbitals in which all those electrons in certain energy levels have certain wave functions. So the potential that is being generated or that has been read is then determined by those particular orbitals which are occupied by those said electrons. It is also the coupling of these orbitals with potentials that lead us to nonlinear equations in these particular orbitals. Now the solutions to these particular nonlinear equations which are found in these orbitals can be determined and are to be determined in an iterative manner which in itself is to be self-consistent. So we have to determine that particular solution to those nonlinear equations in a self-consistent manner which is determined iteratively. Now, we also notice that the Hartree-Fock procedure itself is very similar in its nature to the mean field approach, approach which is found in statistical mechanics. So when one deals with problems in statistics, one approaches certain problems using a mean field theory. It is that mean field theory or that approach which is very similar in procedure to the Hartree-Fock method. Of course, it is not enough for us to just say that and conclude on the issue. We have to further elaborate. This Hartree-Fock method, we do understand that having nuclei and electrons, there must be interactions between those electrons. Now, to simplify the problem, we then neglect those correlations between the electrons to a certain extent. What extent is that? It is the extent that the Coulomb repulsion between the electrons is still considered, but when we consider it in an averaged manner. So we average the Coulomb repulsion forces between the electrons, and that represents the correlations, if to say, or so to speak, between the said electrons. Now, we also have that due to the fermionic nature of these electrons, we have an effective interaction of those particular electrons, in which this particular interaction that is effective also obeys Pauli's exclusion principle. This has to be included into the Hartree-Fock approach for it to be validated, for it does not disobey certain established laws when you're dealing with at a quantum realm or at a quantum level of how electrons behave. So this particular method obeys this Pauli's exclusion principle. That is to say, we have an effective interaction between the electrons, which is also as a result of their nature of being fermionic in nature. They're fermions. Now, the Hartree-Fock method is also very popular amongst chemists, or at least it was very popular amongst chemists, and it has also been often applied to solids. So you see that even solid state physicists can also apply these particular methodologies or this computational method to solve certain problems. Now, without further ado, I'd like to thank you for getting this far in this video, but please don't forget one more thing. Please like and share. Hit that like button, and also please hit that subscribe button for you to be up to date in more content related to this video, related to any physics concepts. This is at the Physics channel, where you interact with physics and physics interacts with you. Bye. See you on the next video.